pleasure to be here tonight. It's for me, a brand new audience, I believe, for most of you. So I'm excited to have a chance to tell a bit about quantum sensing, so this third leg in quantum technologies. My name is Mathieu. I am the co-founder of a startup located here in Basel, a spin-off from the University of Basel. The company is called Qnami, which kind of borrows from the tsunami, but we replace the tsu with Q. So it's not a big wave, it is a quantum wave. So I'm perfectly in the topic for tonight's event. My background is I'm a scientist by training, did 10 years of research in quantum, actually in the different fields. At the time, we were playing with spins, and today we would call that a quantum computer, but it wasn't another life. And in the past 7 years of the existence of Qnami, I've been in charge mostly of the development of the organization, the development of our business activities, and basically recruiting fantastic staff to develop the technology that I'm going to talk about. So, as was said before, generally speaking, our digital economy relies on three pillars, right? We have the communication, we have the computation part, and of course there's the sensing part. And really this is why we think of quantum in these three different flavors. They all contribute to improving the current digital technology. In the same way that you can think of the quantum computer being a better brain, we will think of quantum sensors being better eyes or better fingers. So basically enabling us to capture weaker signals and measure stuff that we haven't been able to detect so far. Now, the interesting thing about quantum sensing is that we are actually leveraging one of the weaknesses of these quantum systems in the technology that we've been talking before in quantum computers. Essentially, we have a very fragile quantum system. They are always fragile. This is what we're not used to seeing quantum mechanics around us. So they are affected by noise. And this is basically a problem that IBM and the others try and solve every day by putting the quantum system in the cold, in the vacuum, making them isolated from the environment. The reason is that as soon as they start to interact with the environment, they basically decohere, as we say in good quantum language, which basically means they lose their quantum characteristics. Now that's the very thing that for quantum sensing we want to use, right? So we want to have a system that we can place in a quantum state, but we will see we will try and measure how quickly it decays, how quickly it becomes bad. That's the fundamental idea of quantum sensing. So this is also one of the reasons why, if you have heard of quantum technologies in the past, you may have heard that quantum sensing is a little closer to application. It's just because it's easier. We don't need the quantum system to be as good as for a quantum computer. We don't need to have thousands of qubits working really nicely together without noise. We can actually already start and do some really meaningful application with a much simpler system in a way. And I'm going to try and exemplify that today with what we do and also what the quantum sensing and quantum imaging space is at right now. And this starts with an opportunity, and the opportunity is in the sensor market. So the sensor market is a large, highly fragmented market with applications pretty much everywhere. We all know that we have sensors embedded everywhere, right? And the Boston Consulting Group did last year a study on that market, and we find that there is a large pool of use cases where the industry really do need higher performance. And that higher performance means higher sensitivity or higher precision, being able to measure either weaker signal, which are diffused all around you, or coming from a very small point in space. So this is the opportunity that we're after. I'm going to try and give 2 or 3 examples so I don't get long on that one slide. One word to say that in quantum sensing, as in quantum computer, there are different technologies that you can use. Several ideas, several companies working on different types. And with no big surprise, they're the same flavor that you can use for quantum computers. What I want to highlight here is it is already not entirely clear, but there are certainly space, depending on what you want to measure, the physical property that you want to measure. It is already clear that some systems are better than others. For example, I'm going to talk about diamonds, which is the first column, nitrogen vacancy for the specialists, where this is being made really obvious right now. So this is the platform that we use at Qnami. We have chosen what we call, or what is called, ND centers in diamond. They are color centers, they are defects in an otherwise extremely pure diamond. So for those who have some diamond jewels, maybe you have some which come with color. These colors are exactly due to small defects that you have in your diamonds. Hopefully you bought those intentionally, and they give a really nice color. In this case here, we work with extremely pure diamond, and then we choose specifically the type of defects that we want to have, and we also choose where exactly that we want to have them. They are, all these defects, each individual defects are going to be the sensors that ultimately measure something in our environment. Why do we like diamond? First, because it's a system that works at room temperature. So it's a system, it's a quantum system that we can make work without cooling. And for sensor application, for large deployment of the technology, it is very obvious that this is a fundamental advantage. There is no point in thinking of cooling any system if you want to deploy it in a car, right? So that's one first advantage. And a second very important one is that even if diamond sounds a bit fancy here, it is actually a semiconductor material. It is a material that we know how to produce synthetically. And I'm not talking about like synthetic, like fake diamonds. They're really extremely pure diamond that you can today buy. They're called green diamonds. You don't need to go to the mine. You can have them fabricated in labs with extremely high quality. And further to that, you can even process that. This is a specialty where Qnami has become really strong. We know how to process these materials using recipes that we borrow from the semiconductor industry. So what all that means is that at the end of the day, it's a technology that we understand how to scale. We understand exactly what needs to be done to go from one prototype to a large volume of these type of materials. We also understand it's really hard and CapEx intensive, but at least there's no fundamental roadblock. This is just to illustrate, we don't need to go into the details. This is to illustrate how we can go into this opportunity. There are parts of that market which are already open today. I think that's one takeaway message. I'm going to talk about one example which is concrete. It is now. We're selling system in that application. And now the two important parameters are the ones with this small star. We basically need to understand to improve on the performance. So this is continuous engineering work to make the system better and better. And we need to work on the form factor. So today the sensors are a bit big, maybe shoebox size. We can make them half of that in a year time or so. Eventually they need to be sugar cube-like or even smaller. So those are the two areas where you need to think, spending your time if you want to unlock these different market opportunities. Now, what are these market opportunities? So here is one example. This is the one we're spending most of our time. The first sensor is essentially a very fancy electric probe. So for those who know the semiconductor industry, they are handling what we call wafers. These wafers are large silicon substrates, which are later diced out, and from there you get the chips that we have in our iPhones. During the production process, you have electrical probers which will basically get in contact with or get very close to that wafer to measure signals and basically check that the chips and the dies and the transistors are working over and over and over. Now, the challenge is that measuring with these electrical probers require that the chip is finished, right? You need to be able to send an electrical current, and then you will see if everything works fine. This is working more than it is possibly conceivable. Otherwise, we wouldn't have that technology out. But still, you need to produce the entire chip before you can test it. And if you could measure these type of signals even before, this would, in many cases, cut the waste. Imagine that your chip is not working, that your process has a flaw. You basically need to go through the whole process before you figure out that there is a flaw. But the flaw could be in the very beginning of the process, right? So there is a constant game, and we're not actually the only one to try and bring metrology, measurements earlier in the quality control chain. But what I'm saying here is that with these quantum sensors, we have here an opportunity to do some of the measurements which today we only know how to do at the very end of the line, do it very much earlier in the fabrication process. This is where we want to go, where we are already today, is not in production environment, because those are extremely controlled and it takes time to get into this environment, but in their R&D, it's the same problem. You're going to design a chip, you have an idea in mind, so you're going to start to produce some of these chips, and you want to cut down, the chips that are not working as soon as possible. So in that R&D phase, we are selling systems with these quantum probes, which allow semiconductor engineers and scientists to test their designs, their ideas with a short loop in the normal cycle. And here is a small picture. This image that you see on the bottom left really is one of these next generation memory, which is being prepared for basically advanced computing. It is an embedded high capacity memory that this company IMEC wants to bring to the market. And what you see, each dot here is one of these memory units. This is something today they just cannot see at this stage of fabrication. And from these images, they get an awful lot of insights that steer their next development. Another example, which I'm personally quite excited about, is with mineral exploration. To support the transition, the technology transition that we're all calling for, we basically need a bunch of new minerals. They're called critical minerals. They are the ones that you need for batteries. They're the ones that you need for electric vehicles, or for photovoltaics, etc., etc. But those are actually quite scarce. And the International Agency on Energy has established that if we want to just meet the goal that we have set for ourselves in terms of sustainability for 2030, we need to open 300 new mines of cobalt, nickel, etc., etc. Now, if we don't want to just, again, take half of the Earth upside down, we need to do a targeted search. And this is a very specific example where quantum sensors are now starting to be used. We're in the pilot phase of that. This is not Qnami, this is a partner company. They are deploying already together with Glencore on site quantum sensors that you can attach to drone. For those who are not familiar with this, it may sound like a natural thing to do, but it's actually a breakthrough in this environment where people are still walking the earth and basically sampling the soil and taking it to chemical labs on top of aircraft, etc. It does accelerate the discovery. At least that still needs to be demonstrated now, but definitely the pilots are going on the mines and on the land that people know. The data shows that we can, with these scans, get what they could already infer with all the other technology that they have, but simply much faster. So I'm very excited about this one. And to conclude, I want to bring an idea of what is the dream in that area, and that is the brain-computer interface. That is a human-machine interface. And the idea here is that with quantum sensors, instead of measuring currents on a chip, what if we could measure current that are actually flowing in your brain? It is the very same principle. It is one step more challenging because those currents in our brain are extremely small. They're also buried a bit deeper. It's a complex system that is going on here. but it is definitely one of the big trends, because in terms of performance, we can get there. In fact, already today, those quantum sensors are deployed, measuring brain activity, not yet capable of doing any sorts of feedback for a machine, but for diagnostics. So if you suffer from epilepsy, and you want to analyze where it's coming from, if you want to find the source of that epilepsy, and if your surgeon is prepared to operate, make an intervention on you, you are very likely going to use a quantum technology that is going to map your brain activity and identify that spot for you. So it's already happening. It's confined to very specific hospitals because it needs a very specific infrastructure. And the dream here is that we can simplify it so that we can start to use it out of the lab. So this is coming. It takes some more years. It will need validation, etc. But this is semi-sci-fi. It is slowly happening. And maybe I will skip that. I think this is my usual word to say that all of that definitely needs this ecosystem to line up. It's a lot to do. The bottom line is that we need investment. And to finish, this is Qnami, this is who we are. So you see that we could achieve already a lot with a very small team. We're a little more than 15 people, headquartered here. We have offices in PSI as well. For those who know, this is where there's this huge synchrotron. They have clean rooms. This is where we have our foundry work. And we're supported with investors, by investors. And if any of you is interested, there is going to be an opportunity for investment service. And I couldn't close without saying that Switzerland definitely has, I'm not Swiss, but I've been around Switzerland for a long time, and I see that Switzerland has absolutely mind-blowing, unique knowledge on quantum. There has been here programs that of a quality that we didn't have outside. It is also frustrating to see that it's going really slow as for the tech transfer of that knowledge. Some talents are lost on the way. Some companies are lost on the way as well because conditions are just not much more favorable outside Switzerland. I think this is one thing to tackle. And of course, the other is it is very important to think sovereignty, but we're in these type of very deep technologies where it is absolutely crucial and essential to work at a continental level to achieve anything meaningful. So here as well, I think we need stronger operation. With this, thank you very much.
Thank you very much.